This is the review of digital logic in preparation for the second exam in Comp 375 at North Carolina A&T State University. Gotta have a quote. This is my very first YouTube video, so please let me know if this works effectively for you. If you have any comments, suggestions, please send me an email. Thanks. The second exam in Comp 375 is going to be on Wednesday, March 18th, starting at 11 o'clock and done at noon. You must be logged on to Blackboard at that time. The exam ends at noon on Wednesday. If you don't do it by then, then you didn't do it. The second exam will cover various topics since the first exam. I'm reviewing digital logic in this video. We will also be covering VLSI transistors, cache memory, memory types, and applications, along with microcode. If you've read these chapters of the textbook and there was material that wasn't covered in class, then it won't be on the exam. On the other hand, if we did cover it in class, it could be on the exam. This is an online exam. You'll be doing it by yourself, and of course, since you have a computer in front of you, you could look up anything you want to. The exam is only 1 hour, and the material will probably fill the 1 hour to complete it. So you're not going to have a lot of time to Google everything. Besides, I'm going to try to ask questions which Google won't really help you a lot with. For digital logic, we have several basic logic functions. There is the AND. AND is true only if both inputs are true. An OR is true if any of the two inputs are true. An exclusive OR is true if only one of the inputs, but not both, are true. There are multiple Boolean expressions and laws. A couple of them that are useful is the distributive law. The AND over OR looks very much like algebra, but the OR into AND is not like the algebraic expression. Both of them work pretty much the same, except changing the operators. De Morgan's law is particularly useful when you start working with NAND and NOR gates. De Morgan's law says that X or Y is equal to not X ANDed with not Y, and then inverting the whole function. It works changing the operators, such as X and Y is the same as not X ORed with not Y, nodding or inverting the entire expression. You can produce many different forms of logical expressions. We're particularly interested in the sum of products expression, where you have multiple variables ANDed together and then ORing those clauses. Sometimes we use the star for AND, and sometimes, like in algebra, we just put two letters together and that represents the AND. We've been using Karnough Maps to simplify the expression. Karnough Maps draws a square where you set ones in all the values that have to be true and a 0 for all the values that have to be false. Sometimes you'll have equations where there are inputs that shouldn't happen, or you don't care if they happen, and in those cases we'll put a D in the square for don't care. So you'll have zeros where it must be false, ones where it must be true, and D's where it could be either true or false, who cares. When you fill out a Karnough map, the order of the variables in the square is important. They're not in normal numerical order. They're in gray code order. So if you look along the top of the square, you'll see it's not A, not B, which is kind of think of it as 0, 0. And then there's not AB, which is like 0, 1. And then we go to 1, 1, which would be a logical 3. And then we go to 1, not B, or 1, 0. The decimal values for all of the squares is shown in the table here. To simplify an equation using Karnough maps, you need to group all the ones into as large a group as possible. You cannot include the zeros in that group. The bigger the group you make, the simpler the equation is. If you can group the ones into a group that takes like 8 of the squares all next to each other, then that's simplified down to one variable. If there's no way to simplify it, then it will take 4 variables to express that square. Now, when you have a D or a don't care, you may group those in the groups, or you may omit them. It doesn't matter if you include them or not, but if you can make a bigger group of ones by including the don't cares, then do it. It will make the equation simpler. Note that the ones or the don't cares may be included in multiple groups. It doesn't matter if they're multiply true, as long as everything is covered at least once. One of my favorite problems is the 7-segment display. We assume we're displaying a decimal number, such as an alarm clock or any other electronic device that uses the old 7 segments. Here's an example with all 10 digits shown. And there are 4 inputs. Since 4 inputs, 2 to the 4 is 16, there are 5 values that are not shown. That would be 10, 11, 12, 13, 14, 15, or if you're doing hex, from A to F. We don't care what those values are, because if we're displaying decimal numbers, they shouldn't occur. So here we're going to try to write a simplified logical expression for the upper right segment, labeled B of the display. And you can see for the number 1, the right side is B and C are on. For number 0, all the outside ones are on. For 3, A, B, G, C, and D are on, and so forth. And you can see from the truth table on the left which ones are on. Basically all of them except for 5 and 6. Here's the groupings. This biggest group is the top and the bottom together. Remember that a table wraps around right to left, so the leftmost side is adjacent to the rightmost side, and top to bottom, so the top row is adjacent to the bottom row. So the top row and both the bottom row together form a big group of 8, which is the not B's. So therefore the not B's pick up most of the ones we have. Also pick up a couple of the don't cares, but we don't care. Picking them up makes this group larger. Then we only have 2 of the squares that we have to pick up. So if we do columns, the not C, not D column on the left picks up that 1 there in the left side. And then for that 1 close to the middle, the CD column picks it up. So there's our sum of products expression at the bottom, which is not B, or not C and not D, or C and D. Now you can convert a logical expression to a gate diagram, very similar to how you might actually implement it in hardware. From a sum of products equations, like we displayed earlier, you can AND all the clauses together with an AND gate, and then the results of those are ORed together. We'll assume that all the ANDs and ORs gates have as many inputs as you like. Here are the gates that we use. The NOT gate, which is a triangle with a circle. The AND gate, which is half round. The NAND gate, which is not AND, it's like an AND with a NOT coming out, is half round followed by a NOT. Then there's the exclusive OR, which is an OR with a line behind it. The OR, which is kind of a half moon. And the NOR, which is the OR with the little circle after it. So that's a NOR gate. NAND and NOR gates are easier to make out of transistors than AND and OR gates, so they're frequently used. Here's an example for the expression X, Y, Z, or not Y and Z. We start with all the values drawing horizontal or vertical lines, followed by their knots as vertical lines. You don't have to do it this way, but it makes the diagrams frequently much neater and cleaner. So if you look at this expression, The topmost AND gate ANDs X, Y, and Z together. The lower AND gate ANDs not Y and Z together. And then the output of those two AND gates go into an OR gate, and that's the result of the equation. Here's another example for an addition circuit. The sum is not easily simplified, but you see we have not X, not Y, C input, or not X, Y, and not the C input, or X, Y, and C, or not X, Y, and not C. And there they are. The four AND gates representing those are all ORed together into an OR gate to give you the sum. The C out is also demonstrated. The lowest AND gate there is the XC, and then the one above that is the XY, and the one above that is the YC. You can do the same equation with NAND gates by remembering that the OR of gates is equal to the AND of the NOTs. So if we replace all the original AND gates with NAND gates, now we have the NOTs of those values, and then we NAND the result. Well, that's the same thing as ORing it. So you can use NAND gates to create this instead of using AND and OR gates. The advantage of this is that NAND gates are easier to produce with transistors than AND and OR gates. We've been discussing combinatorial logic. Combinatorial logic has all the inputs and the outputs are at the same time. On sequential logic, it depends on time. In general, we won't be discussing sequential logic too much in this class, but they're useful to create a one-bit memory. A flip-flop is a sequential logic, and it creates a one-bit memory. Here we have R and S input. When the S is 1 and the R is 0, it sets the output to 1. When the S is 0 and the R is 1, it sets the output to 0. But when they're both 0, it stays the same value. You can combine these with a couple AND gates and a NOT gate to make a D flip-flop. D flip-flops are particularly useful for memory. You have the D input and the Q output. You also generally have NOT Q because it's available. We may not need NOT Q, but it's always there. And so the input is D, and then there's a C input, sometimes called the clock, but better thought of it as enable. When the C is on, then the input D is represented on the output Q. When the C is off, then the output Q has the value that it was last time the input was on. So it remembers when the C is on. When you turn off C, it ignores the input and remembers the last value when you set it. We can often draw flip-flops as a box instead of drawing them as they're a collection of AND and OR gates. And we have a D input, a Q output, and a clock. Don't think of the clock as a time tick-tock kind of clock. Think of it as enable. When the clock is on, then the D input goes to the output. When the clock is off, it ignores the D input, and the output is the value that the D had when it last turned the clock off. You can string several flip-flops together to make a register. Here's an example of a 4-bit register. We could have a 32-bit register if I wanted to draw more. And they have clock inputs, D inputs, and the output is Q. Okay, for the exam, you can expect to be writing a microcode instruction, probably a couple of them. You will be simplifying a Boolean expression and drawing the gate circuit for that expression, and you'll be selecting the proper memory for an application. It's awful hard to draw a bar over a letter. I can tell you because I made these slides. So I recommend using an apostrophe after the letter to represent the not value. So down at the bottom you can see A apostrophe B means not A and B. So use that when you have to write the expression on the exam. Good luck on all your exams.